Okay, hi everyone. So in this example, we're actually given parametric equations where we actually have x as a function of t in this form of log to the base of e of tangent t, while y is equals to sine squared t. Okay, and we're also given the range that is going to be valid, that's from 0 to pi over 2. Okay, and so we're actually supposed to find the dy per dx of the equation in terms of t, and then find the tangent of the curve at point where x equals to 0. Okay, so means that let's find the dy per dx first. So if we have x equals to ln tangent t, okay, so what I need to actually do is to find the rate of change of x with reference to t, meaning that I actually have to do a dx per dt. But in order for me to do it, because this is not in the standard form, let me just first look at substituting tangent t as u. So it means that I'm actually going to put let u equals to tangent t and find the differentiation of it. So du per dt of tangent t is going to be secant squared t. Okay, and we know that in order for us to do dx per dt, so that's going to be equals to d ln okay, maybe I can substitute tangent t as u in this case per dt, or I can actually write it as d ln u per du times du per dt. So now ln u is in the standard form, and I can differentiate it with reference to u. So this is going to be 1 over u, while du per dt, that is actually going to be, as shown here, secant squared t. So 1 over u is tangent t, so if I were to do, so tangent t, sorry, it's 1 over tangent t, so this would then be cos t over sine t, and then secant square is 1 over cos square t. So if I were to cancel this out and cancel, so I'm actually left back with sine t cos t as the denominator. Okay, now let's look at the y function. So y is sine square t. Okay, so what happens is I can again do substitution rule where I let v equals to sine t, so dv per dt, this actually gives me cos t. Okay, so now let's look at the differentiation of y with reference to t, so that I can actually write it as d. So sine square t is kind of like, I can actually substitute v here, so v squared per dt, but what I'm going to do now is differentiate v squared with reference to v multiplied by dv per dt. So v squared differentiated with v, this will become 2v, and dv per dt, so this is cos t. So therefore, if I substitute v back, so this becomes 2 sine t cos t. Okay, now let's look at finding the dy dx. So dy per dx, we can attain it by doing dy per dt multiplied by dt per dx. So what happens is dy per dt is 2 sine t cos t, and dx per dt is 1 over sine t cos t, so means that the inverse of it, this will be multiplying again by sine t cos t. So what I can do is, maybe what I do is I'll brackets this square, because it's multiplying again by the same components. So this becomes 2 sine square t cos square t. Okay, yeah. So I also need to figure out what is the value of t. So when x equals to 0, so when x equals to 0, so tangent t, oh sorry, so when x equals 0, that means that 0 equals to log tangent t. So we know that log 1 equals to 0. So what happens is tangent t would then be equals to 1. So therefore t would be equals to, in order for us to get 1 as the tangent t value, t would be equals to pi over 4. Okay, so if we substitute pi over 4 into the equation of sine t and cos t, so what happens is pi over 4 is 45 degrees. So that means that dy per dx will be equals to 2 times 1 over square root 2 squared. So sine pi over 4 is actually 1 over square root 2. Same goes with cos cos 45 degrees, which is going to be also 1 over square root 2 squared. And what happens is we have 1 over 2 here and again 1 over 2 here. So the 1 over 2 would cancel out with 2. And what remains is the value of 1 over 2. So therefore at point x equals to 0, the dy per dx value is equals to half.